The Nyquist-Shannon theorem tells us that we should sample at least 2 times the maximum frequency in our signal. So the example that we went through earlier where we had a 10 hertz sinusoid, we would need to sample at least 20 hertz in order to accurately reconstruct the signal. And the big question that hopefully you're asking yourself is what happens if I don't? What's the consequence of this? So we did see one example of this already, where we had that 10 hertz sinusoid and we sampled it at only 12 hertz, which is definitely less than 20, and we ended up with this thing that looked like a 2 hertz signal that came out of it, right? So instead of the 10 hertz sinusoid that I would expect, I saw something that more closely approximated a 2 hertz sinusoid. So the basic idea is this. If I sample below 2 times the maximum frequency in my signal, 2 FM, then I'm going to get a false frequency that's less than my sampling frequency divided by 2. So in this case, I was sampling at 12 hertz, so 12 hertz divided by 2 would be 6 hertz. So I'll get a false frequency less than 6 hertz called the alias frequency, and we often write this as FA. Right? An alias is kind of like a fake name, perhaps for a criminal. In this case, it's a fake frequency that doesn't actually exist in the original signal, but shows up in my sampled signal. So let's try to get some intuition behind where this 2 times maximum frequency constraint comes from. So if I sample at 2 times the maximum frequency, I'm effectively sampling every peak and trough of my sinusoid here. So I get all of these peaks and troughs. And if I do a decent interpolation to reconstruct my original signal, I'll actually be able to reconstruct this sinusoid here. So the intuition is that sampling at 2 times that maximum frequency is going to capture all of those peaks and troughs. Right? And ideally, you're going to want to sample much higher than that even, and we'll talk a little bit about that later. And if I'm sampling at something slower, in this case 12 hertz of my 10 hertz sinusoid, I'm missing, in this case, peaks and troughs, and that's what ultimately gets me the poor representation of my original signal. So I missed an entire peak here, effectively missed an entire peak here, missed an entire trough here. And that's why I can't reconstruct the signal in the end. And in this case, not capturing all of those peaks and troughs results in effectively a 2 hertz sinusoid that comes out of that 10 hertz sinusoid that was sampled at 12 hertz. So what's really actually going on here? Well, my sampled signal will have a maximum possible frequency based on that sampling frequency, or FS. And this maximum possible frequency in my sampled signal is defined as the Nyquist frequency, which in this case I'm going to call Fn, and that is going to be that sampling frequency divided by 2. Or I could also think of this as 1 over 2 times delta t, where delta t is my sampling interval. So as a quick example of that, I can think of that 10 hertz sinusoid that I sampled at 12 hertz. If I sample any signal, right, regardless of what the frequency content of that signal is, if I sample any signal at 12 hertz, or an Fs equals 12 hertz, then the maximum frequency in that sampled signal is going to be Fn equals 6 hertz, 12 divided by 2. And in this case, you'll notice I wrote xn in brackets, square brackets here, instead of an x parentheses t, and that's because this is a discrete signal. Right? I have individual samples. It's not a continuous function of time, for example. So I can predict any alias signals that I might get from something called a folding diagram. Right? In the folding diagram, the most important part, I have this x-axis here, and I'm defining fractions of Fn from 0 to 1 Fn. Remember, Fn is my Nyquist frequency, which is half of my sampling frequency. And if I have any signal that I'm sampling here up to that Nyquist frequency, I'll get the resulting signal. So if I was sampling a 4 hertz signal at 12 hertz, for example, my Nyquist frequency would be 6 hertz, half of 12, and 4 is below 6, so that would actually show up as a 4 hertz signal in my sampled signal. Right? Things get more complicated when I get higher than this. So if my original signal has a frequency higher than that Nyquist frequency, I start folding back. So if I'm at 1 1/4 times that Nyquist frequency, I will get an alias signal at 0.75, 3/4 of the Nyquist frequency. If I'm at 1 1/2 times my Nyquist frequency for my original signal, I will have a signal in my frequency in my sampled signal that looks like half that Nyquist frequency. And the same for 1 3/4 will look like 1/4 of the Nyquist frequency, and 2 times the Nyquist frequency. If I have a sinusoid at 2 times Fn, it will look like I have 0 frequency content in my sampled signal. So as a quick example of that, our 12 hertz sampling rate, that gives me a Nyquist frequency of 6 hertz, right? So 1.5 times 6 will give me 9 hertz, so that will look like 3 hertz in the end. So if I have a 9 hertz signal that I sample at 12 hertz, it will look like 3 hertz. And the same thing will continue higher than twice that Nyquist frequency. So, for example, once again, with my 12 hertz signal, if I had a 15 hertz original signal, my 12 hertz sampling rate, if I had a 15 hertz original signal, or 2.5 times that Nyquist frequency, it would look like a 3 hertz signal. My sampled signal would look like a 3 hertz signal then in the end. So this is what this folding diagram is showing us, is that these higher frequencies, when I'm sampling at too slow of a rate, below 2 times the maximum frequency content of that signal, I'll get a much lower false frequency or alias frequency. So those higher frequencies are aliased down to lower frequencies. So as a specific case of that, if I take this line right here, if I have an original signal that's 1/4 of my Nyquist frequency, and remember, Nyquist frequency is a consequence of my sampling frequency. If I have an original signal with a frequency content of 1/4 of that, or 1.75 times that, or 2.25 times that Nyquist frequency, all of these look the same in the sampled signal. And finally, let's look at that specific case that we've been walking through the entire time. I have a 10 hertz signal. I'm sampling that at 12 hertz. So my sampling rate here is 12 hertz. That sampling rate is going to define my Nyquist frequency, which in this case is going to be half of, in all cases, is going to be half of my sampling frequency. So in this case, that means 6 hertz. So now I want to figure out what my input signal frequency is in terms of that Nyquist frequency. My input signal frequency is 10 hertz. So 10 hertz is some factor of 6 hertz. In this case, 10 hertz is 10 over 6 times 6 hertz. And I use 6 hertz here because that's my Nyquist frequency. So this tells me that 10 hertz is 5/3 times that Nyquist frequency. So from my folding diagram, right, and I've written it a little differently. I've written it in terms of thirds of Fn, just to make everything a little bit easier for myself. Right, I'm going in this direction, and then once I get to 5/3 of Fn, I map that down here, and that's equivalent to Fn over 3. So my alias signal is what I'm getting from this folding diagram is going to be Fn over 3. My Nyquist frequency is 6 hertz up here, so 6 hertz divided by 3 is 2 hertz, which makes sense. That's what we actually saw when I sampled my 10 hertz signal at 12 hertz. I saw this aliased frequency at 2 hertz.